welcome to another Generative Components tutorial. Today we're going to look at how to incorporate the Optimizer into your workflows. We'll look at some simple examples to get the Optimizer node set up and running, and then we'll put the Optimizer to work with a more complex scenario of generating an optimum sun hood for a window. So let's get started. Here we are in a new DGN file called simple_line. To start, let's change to a top view and then set the view style to wireframe. Clicking on the point tool and clicking yes and OK to create a base CS, I'll place 3 points generally spread along the x-axis. For the last point, I'll change the x value to 5000 and set the y and z values to 0. Dragging in a slider node and changing its name to x1, I'll double click on it to change its default settings. Setting the minimum to -5000, maximum to 5000, the resolution to 250, and let's set the value to 2000. And finally, we'll set the tick interval to 500. I'll now right click on this node and copy and paste it a few more times to be the x and y inputs for the other 2 points. For the y values, let's change the values of the sliders to be 500, the minimum of -1000, a maximum of 1000, and the resolution of 100. And we can change the name of this to y1. And we can do that for the other slider for the y input, calling that one y2. Now we can link up y2 and x2 to the point 2 inputs, and y1 and x1 to the point 1 inputs. We'll also set the z values to 0. To make it easier to see, I'll just adjust the sliders a bit to get the points separated a bit. Now dragging in a curve node, we can select a polyline from the curves from point set option and then click inside the input box for the point set. We can now drag over the points including the base CS to create a curve. Now we have a line string that is fixed at each end, but we can adjust the sliders to move the middle 2 points around. To make it a bit clearer, I'll right click on the base CS and point 3 and turn off their visibility. Now we have the basis for a simple optimization run. In this example, I'd like the Optimizer to find the shortest length for the curve that we just created. Now we already know this to be a straight line, but this will be a good way to test out the Optimizer with a known result. So to do that, I'll drag in one more node to just indicate the current length of the line. So dragging in a value node, I can link it up to the curve1 node and put in .length to show the length of the curve. Now if we drag in an Optimizer node, we can link up all the sliders to the parameters input, and then we can link up the value1 node to the minimization input. And if you have tried to get the Optimizer working in the past, this is where you might have started to scratch your head a bit. We have all the inputs we need, but we're still getting an error. This is because the inputs for the Optimizer are expecting a list. So all we need to do is place that value1 inside curly brackets for the minimization input. So once this is done, the error disappears and we're ready to run the optimization. So reading some of the help files and the online documentation on the Optimizer node, it is based on a genetic algorithm. So the settings are based on things like population, mutation rates, and other genetic inputs. For the examples in this tutorial, we'll be running the Optimizer in its default settings and just focusing on getting it running and looking at the results. So with all the inputs done, let's click on the Run button on the Optimizer and it's indicated by the running figure. This kicks off the optimization process and will build up the population and the generations until the completion criteria have been reached. And you can see the values of the sliders are jumping around as different combinations are tested. And for this example, it was under a minute and it ran through 14 generations. When it is finished, you can click close and then a results window will appear. Here you can see as we only have one objective, there is a straight line of results. Each of the dots represents a possible solution. And if you click on one of those dots, the values for that solution will be displayed. And you can see the results for this solution are extremely exaggerated as it was testing all the combinations of the sliders. As we move down the line, however, towards the 0, 0 corner of the graph and select the last dot, we can see the value here gives us a straight line as we'd expected. As we move further away from this corner of the graph, we get lines that are longer. So that is a good result and confirms the theory that the shortest distance between 2 points is a straight line. But we all had predicted that before we started, but it's a nice way to confirm everything is working as expected. So opening up a new file called path_line, again, we will set the view to top view and the view style to wireframe. Clicking on a point tool again and clicking yes and OK to set up the base CS, let's drop down just 6 points this time. Now dragging in a B-spline curve node and setting its method to by points, we can click on the input box and select the points to create the curve. I might just adjust the endpoint to make the curve a little bit nicer. And while we're at it, we can have a quick look at the X and Y values of the last point, and it gives us an idea of the range of the sliders I might place in shortly. For that, let's drop down 2 more points that we will be using for our optimized curve. Now we can drag in a slider and double click to access its values. And let's set the maximum to 15,000, the resolution to 100. The value can be 500 and the tick interval can be 1000. Now we can right click and copy this slider and paste it 3 more times. And let's rename the sliders to X1, Y1, X2 and Y2. With the sliders set up, you can link them up to the last 2 points we just created, setting the Z values to 0. We can now adjust the sliders to place in the points in a better location. And let's rename the B-spline curve to Path Curve. And dragging in a new B-spline curve, we can now set its method to by points. And this time, click inside the input box. Let's hold down Control and select point 1, point 7, point 8 and point 6. This is another great method of getting the points in the desired order without having to type them in or try and select them. Just simply hold down Control and select them in the view. Let's rename this B-spline curve to Average Curve. And now for this example, I thought we could use 2 goals. One could be minimizing the length of the curve, as we did in the last example, but another might be trying to keep this curve as close to the other curve as possible. So to do that, I thought I could place a series of points along both curves and then measure the distance between those points. So let's drag in a point node and rename that Points on Path and change its method to by number along curve. And linking that up to Path Curve, we can set that number to 6. Now we can right click and copy this node and changing its name to Points on Average Curve and changing the curve input to average curve. Now to measure the distance between the points, we can use the value node and just type in distance and then open brackets, then input the 2 point nodes. So it'll be points on path, comma, points on average curve, and then close brackets. And here you can see it results in a list of distances, which are the corresponding distances between the points on each of the curves. So point 1 on path curve to point 1 on average curve, and so on. Now we could input this into the optimizer node, but I'd like to use this as an overall distance between the path curves. So let's drag in an operation node and let's link up the value 1 node to the subject and choose sum from the operation. And we can rename this to total distance between curves. There's only one other item to drag in, and let's drag in a value node and input average curve.length and rename this to average curve length. Now it's trying to drag in the optimizer node, and we can link up the sliders to the parameters input, and we can link up average curve length and total distance between curves to the minimization input, and the optimizer is ready to run. So first I'll give this a file save to make sure we don't lose anything. One thing I did notice in my testing is that after an optimization run, the file can sometimes not record any changes to the file, and I'll have to investigate further. But just to make sure you save and commit the changes to the transaction window before you run the optimization. So clicking on Run, you can see some of the changes as it runs through the options. And this took around 90 seconds to complete. So clicking on Close, the graph will open, and this time we have a curve of sorts. This is showing the 2 objectives we set up, average curve length versus total distance between curve. So clicking on a dot will show you the results of that solution. As you move further to each end, you will have the bias of that result. But there are some interesting results around the middle, where the distance between curve is similar, but the curve length changes. I think this starts to show some of the power of the optimization to find the potential solutions for questions or objectives that have multiple possible outcomes. So for the final example, I thought it would be good to take this theory to a more practical solution, the optimization of a sunhood for a window. So starting a new file called window_sunhood, I'll start by clicking on the coordinate system to set up a base CS by clicking yes and OK. I will, however, drag in a new coordinate system and change its method to by origin rotation about coordinate system. So linking this up to the base CS, we can set the rotation axis as the Z axis. For the rotation, let's set up a variable by typing in rotation to north equals -20. And you can see that a new node appears that is just a value node, but it's a quick way to set up some simple variables. This will set up our rotation of our window to north in plan. We can rename this node to window CS, and let's drag in a point node and set its method to by direction and distance from origin. The origin will be that window CS we just set up, and the direction will be window CS.x direction. And if we expand the dropdown, we can pin out the distance and set up a new variable called window width equals 2000. And then we can change this to window width divided by 2, as we'd like the window CS to be on the bottom center of this window in this case. Renaming this to point 1, PT1, we can then copy this node, paste it 3 times to form the 4 points of the window. So changing point 2 origin to point 1 and the direction to window CS.z direction, the distance can be window height equals 1200 as a variable. Point 3 origin can be point 2, and the direction can remain at x direction, and the distance can be set to minus window width. For the final point, the origin can be 0.3, the direction can be set to Z direction, and the distance will be minus window height. With the 4 points created, let's drag in a polygon node and link up the points we just created as the inputs for the polygon. For the final step, I'll drag in a B-spline surface and rename it to window surface. And we can set its method to from closed curve, and we can link that up to that polygon one we just created. To make it a bit easier to see, let's open up the general inputs and set the color of this one to colors.blue. Now we have a window set up, let's create 4 lines that could be the basis of our sun hood. We can drag in a new line node and set its method to start point, direction and length. The start point can be point 1, the direction can be window cs.y direction, and for the length, let's drag in a new slider and rename this to length 1. We can double click and to change its settings, and we will set this to a maximum of 1000 because that'll be the maximum width of our sun hood, a minimum of 50 because I thought we'd keep a minimum value. We can set the resolution to 50 and the tick interval to 50 as well. For the initial value, I think I'll start with 500. Now we can link this up to the line length input, and let's rename the line to hood line 1. And then we can select both the hood line and the length 1 and copy and paste it 3 times to make the other lines. Now it's just a matter of changing the start point for each of those to be 0.2, 0.3 and 0.4. With the line set up, we can drag in a B-spline surface node and rename this to sun hood. The method for this can be loft curves, and we can select the lines we just created as the inputs. Now we have a nice 3-sided sun hood that can be adjusted using the sliders we just linked up to those line lengths. So the sun hood is just the model part. Now we need to source some sun information, and for that I utilized a website called sunearthtools.com, and from here you can download solar information from anywhere around the world. And I downloaded some information for January 15, which is for Sydney one of possibly the hottest day of the year, and for the data I set it up to be every 30 minutes. So I ended up with a good solar data array for around 6:30 AM to 8 PM, and I saved this file as a Excel file. To access the information, I thought I could just reference this spreadsheet, and then I could alter the times to test different solar positions during the day. So dragging in an Excel range node and renaming it Excel Sun Data, then set the Excel file input to the file name, and I call that sunpath-daily-jan15.xlsx, and I put that inside quotation marks. For the sheet name, it's just called sunpath daily, and that's also inside quotation marks. And the range I wanted to reference will be inside quotation marks, and it'll be B6 to D33. This reads the Excel data, and you can see from here it'll provide the elevation and azimuth at each time interval. So we can change the time easily, I'll drag in a new slider and I'll change its name to hour selector. For the settings for this slider, I'll adjust them to be a max of 20 or 8 PM and starting at 6.5 and a resolution of 0.5. And this will allow us to select each half hour from 6:30 till 8 PM. To target the correct data, we can use a value node and then use an expression. So it'll be from my sun data, which is just a variable I called it, in Excel's sun data, which is the Excel node, dot value, so we want to look at the values, where my sun data in square brackets 2, so we're working out which column of the data we want to deal with, equals, and then hour selector, which is our slider we set up to select the hours. And if we click apply, you can now see we've filtered the Excel data by the hour selector slider. So let's rename this sun data. I thought as a test to see if the sun hood is protecting the window, we could draw some lines from various points on the window at the correct azimuth and elevation and check and see if they intersect with the sun hood. Then we could count the number of intersections versus the number of lines. We can get a general percentage of shading for the window. A good way to do this is to set up a line in a location away from the window using a couple of the coordinate systems to set the rotations, and then we can draw the line. Then it's easy task to copy and transform this line onto the window. So I'll start with a new point in the top view, just off to the right of where I created the window. And I'll just drag that node down next to the solar data and rename it Ray Point. Now let's drag in a coordinate system node and rename it to Ray Azimuth CS with the method of by rotation about coordinate system, and set its origin to be the Ray Point we just created. And for the rotation, we can use the sun data node, but for this, that information is in an array format. So let's use sun data.flatten and open and close brackets in square brackets 1, as this is the column of data that contains the azimuth. And for the axis, we can set that to the Z axis. Now you can see in the top view, it is rotated to the left or anti-clockwise, which is a little bit different to the way the data has been saved in our spreadsheet. The azimuth is actually read from the north and then rotates around in a clockwise direction. So let's add a minus sign before the rotation angle. Next, we need the elevation. So let's drag in a new coordinate system and rename this to ray elevation CS and set it to by origin, rotation, and about coordinate system again. The origin and coordinate system will be the ray azimuth CS that we just created. The rotation will be sun data.flatten in open and close brackets in square brackets 0. And finally, the axis for this will be the x-axis. Now we can draw a simple line by dragging in a line node and renaming it sun ray with the method of start point, direction, and length. And the start point will be the ray elevation CS, and the direction will be the ray elevation CS dot y direction. And the length for this just needs to be longer than the window that we created. So I'm going to set this to 5000. Now we have a line set up that is projecting at the correct direction. We can now set up some points on the window surface. So dragging in a new point node and renaming it to sample grid, the method can be set to by UV parameters on surface. And the surface will be the window surface that we created earlier. And for the U point inputs, let's open up the editor and type in a series. This will be series, open brackets, 0.05, 0.95, 0.1, and then close brackets. We can copy this and we can paste it into the V inputs as well. Now we have a line of points, but we can right click on that node and select switch replication style, and we'll get all combinations of the series. This will set up a series of points that starts at 5% inside the surface and then finishes at 95% in steps of 10%. This will eliminate the errors of lines being projected right from that junction between the sun hood and the window surface. So to get all the sun rays onto the window, it is now an easy task of dragging in a new line node and setting its method to copy, transform geometric contents. The node to copy will be sun ray, copy from will be the ray elevation CS, and the copy to will be the sample grid we just created. And there we have all our lines created. This saves replicating all the coordinate systems that take up more memory, and we can just replicate the lines themselves. So let's rename this one to sun rays. Now to check if the sun rays intersect with the sun hood, we can check that by generating points and using the count. But I found sometimes that this is not totally correct, as you need to ensure that the point is successfully created. One way to ensure the correct number is to write your own function and just return a count of the successful points. We don't even need to create the points themselves in the model. So dragging in a function call, and by clicking on the lines to access the editor, we can click yes to create our own custom function. In the editor, I will delete the word void and start writing our simple function. For the inputs, first we will have the lines. We can start with line, and then we will call this input sun rays. And then we'll have the B-spline surface, and we can call that input sun hood, and then we can close brackets. First, I like to start with the outputs, and that will be a count or just an integer. And I'm going to call this my int count equals 0, and then semicolon. So then we need to start some loops to dive into that array of lines that we have. So typing in 4 and tapping tab a couple of times will auto fill out the line. For the count, it'll be input sun rays dot count with a capital C. Now we can jump into the second loop straight away. And for this, again, we can type in 4 and tap tab a couple of times, and then we can change the I over to J. And for the count, we can use input sun rays in square brackets I dot count with a capital C. Now we're dealing with just a single line. So let's start creating our points. So we start with a point, and I will call this my point equals new, and then point, open and close brackets, dot at curve surface intersection, and then open brackets. And then we need just to provide the curve and the surface, and that will be input sun rays in square brackets I, square brackets J, comma, input sun hood, and then close brackets, and then a semicolon. Now we would like to check if that was successful. So we can use an if statement. If, and then open brackets, my point dot success equals true, and then close brackets. If it is true, we'd like to count that one. So we'll open up the if statement by using the open and close curly brackets, and we can increment the count by using my int count equals my int count plus 1, and then semicolon. Now all we have to do is return that count. So just before the last curly brackets, we can type in return my int count and then semicolon. So we can click apply, and we can link up the inputs. So we can link up sun rays to the input sun rays and sun hood to the input sun hood. And you can see we have a count. At this stage, we can turn off the lines and the point grid to make it a bit faster in the view. And we can rename that function call to intersection count. Now, if we alter the sliders, you can see the count changes. As a last step for this, I might drop in another value node and call it percentage shade and open up the editor. And this is just a simple maths equation. Open brackets, intersection count divided by sun rays dot flatten, open and close brackets dot count, and then close brackets times by 100 or star 100. And we get a simple percentage. And if we drag the slider to make the sun hood larger, you can see we get 100% coverage. With that all done, let's drag in the Optimizer node and connect the parameters up to the sliders. For the maximum, we'd like to link up the percentage shade, as we'd like that to be maximized. Remember to place this inside curly brackets. Now I'd like the sun hood to be the smallest possible, so for the minimize settings, we're getting it up to the sliders, or we could drag in a value node and link it up to the sun hood and get the area of the sun hood, as you can see here, but the value is very high, and I'm not sure how the resolution works yet in the Optimizer node, if this would throw out the calculations or something. So what I might do is just delete this node and drag in an operation node and link up all the sliders and then sum them together. And let's call this total sun hood lengths. Now we can link this up to the minimization input, remembering to put the curly brackets around the input. So now we're ready to run the optimization and see what it does. So remember to save. And what I might do is just move the optimizer and the other value nodes down so we can see them all adjusting while it's running. And we can turn off some of the coordinate systems to make it a bit clearer. And then we can click run. So this took about 9 minutes, and the results are okay but not overwhelming. And this is probably due to the high probability of success of shading at the time of day I selected. But you can see if we click on different results, we have vastly different options, from the sun hood ranging from 82% to 100% shaded. So to give it a bit more of a test, I changed the time of day and reran the optimization. And if you click on invert on the maximizations button, and we can look at the results that are closest to the bottom left corner, which is heading towards the shortest sun hood but the most shaded. And if you hover over the dots, you can see the values for each dot. And here you get a total length of 1,155 with a percentage shade of 65%. And if you click on that, you can see the results of the sun hood. So if I change the view to a shaded view, you can see it even better. Clicking on the results lower on the graph, like this one with 98% shading and a total length of 1,549, the result is looking quite interesting and providing a very high amount of shading. So there's a simple introduction into the Optimizer node and how you can interpolate its results. So next time we might delve deeper into the optimization algorithm and what impacts changes to the settings have to the outcomes we get. Hopefully you'll find a way to incorporate this into your next project. Until next time, thanks for watching.